Hello everybody, Adam Lusek here, and today we're going to look into language model merging, essentially taking two or more language models and combining their weights together to create one merged model. And model merging answers a very interesting question. If you have two or more task-specific or fine-tuned language models, if you combine them mathematically or algorithmically, can you actually transfer both of the fine-tune abilities into one specific model? And as it turns out, this is possible. And so lots of researchers have started experimenting with different ways of actually combining model weights together to push both generalized performance of language models and then also transferring skills between language models to one centralized one. And this has become particularly interesting because it's a way to get more out of your language models without having to do additional fine-tuning or additional training. So over the last few days, I've been experimenting with merging different kinds of fine-tuned language models across all different kinds of architectures and techniques to put together some resources to explain exactly what and how this is done. Our main tool of choice here is going to be Mergekit. It's an open source repo from RCAI that allows you to implement a whole bunch of model merging algorithms super easily across all different supported architectures. We'll get into actually using this and merging a model ourselves a little bit later into the video, but first, let's go over the different merging methods. And before we jump into the first method, I'd like to give a big shout out to Julian Simone here, who put together some wonderful deep dive videos into each one of these methods. If you're interested in looking at more specifics of how each one of these works, I definitely recommend checking this out, as I'll be giving more of a high-level overview in this video. That being said, let's start with the first method, which is the linear or model soups method. And the idea behind model soups is taking one model and fine-tuning it on a bunch of different data sets. Once you have all of those fine-tuned models, you add up all of the weights, calculate their average, and then ta-da, there is your new model soup merged model. And the weights in this case, and going forward when I refer to the weights, are just the numerical values that are learned during the training process that contribute to the big equation that is the language model. Essentially, these are what's actually being tweaked behind the scenes as a language model is doing its learning through training, and these are what are being actually mathematically manipulated during the merging process. Within their research, they have two kind of different ideas of the soup. They have the uniform model soup and the greedy model soup, which I kind of like the name greedy model soup. But essentially, the uniform soup is taking all of the model weights and averaging all of them. The greedy soup, however, is taking the weights one by one, and as you average them, running a test and only keeping the models that actually improve accuracy on whatever testing data set you're performing. So, it doesn't really get more simple than this. Just taking all of your model weights and then averaging them together to create one final model. Taking this one step further is our second method, which is also funnily named Slerp, or Spherical Linear Interpolation. And the problem that the Slerp algorithm is trying to solve is two-part. The first is that with just pure averaging, we tend to get rid of very small and very large weights, or sort of diminish the magnitude of these weights. And then the second part is that the actual internal workings of these language models operate on sort of this high dimensional space. And so introducing a new dimension during the calculation of these averages with something like a sphere here can help preserve more of the geometric space that all of these weights and embeddings actually are in. And this is all a bit of a confusing way to say that the Slerp algorithm essentially better maintains the shape of the language model and also the strength of the different weights internally, whereas averaging would generally distort or flatten this. Looking at a little bit of a more mathematical example here between linear and spherical interpolation, you can see that this linear side, which you can think of as almost more of the averaging here, loses a lot of the different shape and the different magnitude here that is captured when doing this, thinking about it as a sphere. The same idea applies to language models, where the language model's knowledge is almost captured internally with these different directions and magnitudes or strengths, and the calculation as it kind of goes through the neural network is guided by the different strengths and the different directions that these numbers are taking it in. So taking those into account with spherical interpolation helps to actually maintain a lot of the guidance that the language model is doing during its predictions. It's essentially the same idea as model soup. However, this time we're doing all of the calculations in 3 dimensions on a sphere. Enough about Slerp and soup. The third method that we're going to be looking at is task arithmetic. And the big idea that task arithmetic introduces is the idea of the task vector. And the task vector is essentially if you take a pre-trained model, something like Gemma 2, and then fine-tune it on a task, let's say Twitter sentiment classification. What you now have is a base model and then a fine-tuned model. You can compare the weights between the base model and the fine-tuned model to figure out what actually changed. And so all of those deltas in between the weights between your base and your fine-tuned model become what is known as a task vector. Essentially, the task vector encapsulates all of the updates that happen to the base model during its learning of or fine-tuning on a new specific task. In theory then, if we've isolated all of the updates and changes and how much it's changed to each weight into its own specific vector, we can take that smaller number and then just add all of those changes to some other base model, essentially taking the task and adding it to the weights of another model, and then that model should, in theory, learn the task. This is useful because it only isolates the necessary updates for the implementation of the task on the model. You don't actually have to worry about all of the extra parameters and weights that are part of the base model. You can just focus on the task. Thinking back to our example of our Gemma model that's been trained on Twitter sentiment classification, using this method essentially looks at the base model and then the change to the fine-tuned model, isolates all of those updates into the task vector, which represents the learned ability for Twitter sentiment classification, and then we can apply that to some third model, let's say a Gemma model that's been trained on Reddit post sentiment classification data. We can take the task vector for Twitter sentiment classification, add it to all of the weights of this Reddit model, and then essentially our hope is that it now knows both the task of Reddit sentiment classification as well as Twitter sentiment classification. And this method is kind of cool because it allows us to do 2 other interesting things with it. We can almost extract whatever fine-tuning has happened to a model into some sort of specific set. So in this case, Mergekit actually supports LoRa extraction or low rank adaptation from parameter efficient fine-tuning. And then also, instead of adding, you might even want to subtract the task vector from a model. And one of the specific examples that they have here is making a language model produce, less toxic content. So lots of cool ways to think about actually using this when you're able to isolate then the updates between a base and task-specific fine-tuned model. And the fourth method that we're going to be looking at is called ties merging, or trim and elect signs merging. And what the ties method attempts to resolve is the issue that existing merging methods kind of ignore the interference between different parameters of different models. More specifically, they ignore redundant parameter values and then disagreements of signs. Looking at this figure here that goes over the different types of conflict, we have 3 examples, one of no interference, one of a redundancy, and one of a sign conflict. So if we look at the original values, which will have some sort of sign, either positive or negative, and then some sort of magnitude, which is, essentially how large the number is. Looking at this first part, we see no interference between model 1 in pink and model 2 in purple here. When merged together, they become, roughly around the same value. Nothing too much to complain about there. The first conflict comes in, however, looking at the middle here with a redundancy. Looking at the model 1 versus the model 2 values here, you can see that they're pointing in the same direction. They have the same sign. However, their magnitudes are different. So model 1 has a very small magnitude, but model 2 has a pretty large magnitude in comparison. When we take the mean or the average between them, it reduces greatly the actual magnitude of model 2 down here. And this could be detrimental, as this magnitude might be something that was learned during the training of model 2 that is super important to keep around. And then the third conflict is a sign conflict. Looking at these 2 here on the right now, we have model 2, which has a super large magnitude going positively, and then model 1, which has a little bit of a smaller one going negatively. When looking at the mean, this actually results in a very small positive value. And essentially, it is very, very much flattening the large magnitude of the model 2 weight here. So the trim and elect signs merging method aims to mitigate a lot of these conflicts during the merging process. So hopping over to this figure here that shows 3 models being merged using the ties method, we first start with the task vectors from all 3 specific models. The first step then is to trim the values based on their magnitudes. And you can see this in action going from just all of these task vectors, and then everything that's been dotted out is considered a redundant value or doesn't meet the cutoff and is then trimmed. So we are left then with our trimmed task vectors here. Now that the trimming has been done, we have to elect signs. And then this, of course, is going to be done through a comparison of the values. So as we can see here, this purple value and this purple magnitude is much larger than the pink one for this middle parameter here. And if we look at the align values box here, we can see that we'll be getting rid of the pink one. This relates in a sign vector that indicates at each parameter what sign, either positive or negative, we want it to be. This is then all merged, removing all of the values that don't have the right sign into our merged task vector. You can then use this task vector to apply to a base model, similar to what we did with task arithmetic. Our 5th method now comes from this funnily named paper, Language Models Are Super Mario. However, the actual method itself is called DARE, which stands for Drop and Rescale. And what the researchers behind DARE realized is that most of, if not almost all of the updates to the parameters that you do during supervised fine-tuning are actually not really needed. They found that you can remove almost 90% of the task vector parameters before having a drastic cutoff in performance. So the DARE method aims to get rid of or drop a large percentage of the parameters in the task vector and then rescale the ones that remain to hopefully maintain performance at a much, much smaller task vector size. So taking the task vector from a fine-tuned model, they drop some random percentage. For this example, let's say 90% of the actual parameters, zeroing them out, and then rescale by a factor of 1 over 1 minus the percentage. So in the case of 90%, that means that we would rescale the remaining parameters in the task vector by 10 times. And they found that when merging this created task vector back into the base model, it maintained its learned ability from fine-tuning to almost the same degree. And one of the interesting things to note here is that the DARE method can actually then be applied with additional methods like ties when merging back into the base pre-trained model. And of course, Mergekit supports doing DARE with ties or without, which would just be general linear task arithmetic methods. Our 6th method now is called model breadcrumbs, and it's an advancement on the task arithmetic method. And what this method does is it takes our foundation model, and then once we have all of our different fine-tuned models, we take the weights of the fine-tuned models and subtract out the pre-trained model weights. This gives us this trajectory for each fine-tuned model. And then once we have the weights from each fine-tuned model, which they're calling trajectories, they apply a absolute value mask to the outliers. So essentially, just the outliers of both extremely negative and extremely positive get set to 0, essentially meaning that we're just going to be using the base foundation model's weights whenever those are removed. All of the remaining weights are then added together and then applied on top of the foundation model. And this creates what they are calling the multitask model at the end. So as you can see, similar to task arithmetic, where we extract the task vector out from the fine-tuned models and then do some sort of manipulation with that, we're doing essentially the same thing, grabbing the task vectors for each fine-tuned task-specific model, masking the outliers, adding them all together, and then applying them back to the pre-trained model. This is generally not added specifically directly, but added with some sort of scaling variable. So you might drop everything down to 10% of their values and then add that back to the weights of the foundation model. And similar to what we just did with DARE, since we're adding the task vectors back to the foundation model, we could also apply ties at this time if we wanted. Our seventh method here gets a little bit in the weeds of math, but it's called model stock. So we've upgraded from soup now to stock. And what the researchers sort of observed when looking at different fine-tuned models is that all of the underlying vectors within the model tended to reside, as they say, on a thin shell. So essentially, all of the vectors are pointing in some direction, and you can imagine it almost as, in this 3D example, all of the vectors landing on some sort of sphere. And this is getting pretty abstract, but the main idea behind this is that if you have a bunch of points that lie on some sort of surface as you're undergoing the same kind of fine-tuning, it's likely that the most optimal or accurate kind of direction that you should be going is at the center of that surface. And if you really think about it, considering our model soup method, where we're taking a bunch of fine-tuned models and then averaging them together, this is almost essentially what we're doing. We're trying to find the average of where these vectors are ending up or getting closer and closer to that calculated center. And so the researchers here decided to cut out all of that work and realized with a little bit of geometric thinking, if you have 3 points on an object, you're likely to be able to approximate with high accuracy the center. So that's exactly what the model stock algorithm is doing when looking between the actual vectors of 3 tuned models. This allows them to do essentially the same thing that model soup is doing, but with a much smaller sample size of models. Method 8 then is DELLA merging, or drop and rescale via sampling with magnitude. And it uses a lot of the same ideas behind DARE and ties. The first step then is the drop step. And this is where the uniqueness of DELLA comes in because they have their own mag prune, they call it. And essentially what it is it's calculating a probability that a parameter will be dropped based on its magnitude. If we go down to this figure right here, we can see a little bit of what that means. For a vector with a larger magnitude, it has a smaller probability of actually getting dropped, and then the smaller vector magnitudes have a higher probability of getting dropped. And so once those probabilities are calculated, they then go through each one and then flip a coin with a Bernoulli distribution of that probability to choose whether or not to randomly drop it based on the probability of it being dropped. So in this case, it is more likely for the smaller magnitude vectors to be dropped and less likely for the larger magnitude vectors to be dropped. However, there is still that small chance, as it's being kind of randomly done, for a large vector to be dropped and for a small vector to stay around. The remaining step follows exactly what ties does with electing the signs, and then all of those parameters are averaged, creating your merged final model. And so with all of these mathematical ways of actually doing all of this merging and task vector manipulation and whatnot, you're probably wondering, is it possible to just take out layers from language models and then stitch them all kind of together? And the answer is yes. It's called Passthrough, or what has been coined Frankenmerging. This method is, of course, not as reliable as a lot of the other methods because they all tend to have a common architecture when running all of these operations, but a lot of interesting things are being done with the pass-through method. We're seeing stuff like Goliath 120B, where this guy took 2 fine-tuned Llama 70B models and then combined different layers together via pass-through to create this absolutely massive 120 billion parameter model. And even more recently, a 1 trillion parameter model by Maxime Lebon here, who just combined a lot of Llama models together. So it's quite an interesting and experimental method, and still much to be discovered about stitching together both the similar and different architecture layers to create these Frankenstein almost models. And so to round us out with our 10th and final methodology here, I wanted to talk about the mixture of experts, which of course first came from our lovely friends over in France, the Mistral AI team, when they released Mistral 8x7b, and essentially follows this architecture. And their idea was to combine all sorts of specific fine-tuned models as they are all together into one large model, but instead have some sort of routing and gating mechanism where when a user enters a query, it can feed that query through to the specific expert, hopefully having that expert field most of the predictions being made internally in the language model, thus improving its performance on very specific areas. This is a little bit different from the model merging that we've just been talking about, because essentially this is kind of combining all of the weights of all of these models together, not necessarily merging the specific ones to create one model of the same parameter size. In terms of the types of mixture of expert setups, there's two main ones. There's a sparse mixture of experts, which is actually what Mistral 8x7b is, and a gated mixture of experts. The sparse setup, which is what Mistral 8x7b follows, replaces the feed forward of the actual underlying neural network so that the user query can actually go through a few different experts within the mixture here. On the contrary, a gated approach acts more like a router, where it will take the user's query and then route it towards whichever expert it believes is best to process that query. And at the time of making this, Mergekit only supports actually creating gated mixture of experts, so you'll have to have some sort of routing gate when putting these together. That being said, now we've covered all of the different available merging methods that are within Mergekit. If you've made it through all of those and found it interesting, congratulations, big kudos to you. However, I do want to reiterate that if you want a very comprehensive deep dive into all of these and see where a good chunk of my understanding actually came from this, I highly recommend checking out Julian's video series here on model merging. I'll have that linked in the description below. Great. So now with all of the methodology out of the way, let's take a look at how you can actually use Mergekit to merge some models yourself. I first wanted to show 4 examples of 4 different architectures and 4 different model merging techniques that I've put together over the last couple days. The first one is using Gemma 2 2B instruct, the 2 billion parameter model. And what I did here is I found 2 fine-tuned 2B models. One is this funnily named Sauerkraut LM, which is more focused on speaking German, and then one that is more focused on speaking Chinese. And my idea was, what if I combine these two to give it more of a multilingual capability between English, Chinese, and German? So I used model stock to put this together with this configuration, and we'll go into how to actually run these configurations in a second here, and created Gemma 2 2B Chinese German. So now the hope here is that it's learned all of what the sauerkraut and the Chinese model have done and put it all together into one final merged version. The second example that I have here is actually taking 2 Llama 3 8B models, one that was specifically fine-tuned on coding, and then one that was also specifically fine-tuned on SQL, and merging them together using spherical interpolation, or the Slerp method. The idea behind this one was, if we have a strong coding base, but want it to be something like an expert in writing SQL code, why don't we take the coding base and then merge on top of it the SQL coder? So to do this, I used the spherical linear interpolation configuration right here and ran it through Mergekit. The third example here is a bit of a funny one. I took Phi3 Mini 128K instruct, and I found that someone had released a checkpoint called Phi Marketing, where it was partially trained on a lot of marketing data. And then I found this other one that was designed for emotional intelligence conversational AI models. And so I thought, what better way to improve some marketing methodology than adding in that deep emotional understanding, which is exactly what I was trying to do here with these two Phi-3 models. And to do this, I used the DELLA method. And the fourth and final example that I have here is what I'm coining Mistral 4x7b. 7 billion parameter Mistral models that have been fine-tuned, one for just a base, very good generalist model, one on different medical understanding, one on math, and one as a writing partner, and putting them all together into this 24 billion parameter mixture of experts here. So for our example here, I'm going to walk through actually recreating the Phi-3 Mini Emo Marketing DELLA version. So to start, the first thing to understand about Mergekit is that they automate actually a lot of the merging for these methods. But you have to get a few things right. You need a clear configuration file that follows exactly what each method is expecting. And then also you have to be aware of the different architectures of your models. The most important thing really is understanding the architectures, because you can't just combine here and there all sorts of different architectures and expect it to work very well. The best way is to find one specific architecture and multiple of those fine-tuned models and then combine them together. So up here in the data and architectures file in the GitHub repo, you can actually see all of the different architectures that they support here. So in our case, we've already identified that the architecture we want to use is the Phi-3 architecture. Specifically, we'll be looking at fine-tuned models of Phi-3 Mini 128K Instruct. And as mentioned before, we have our two candidates. We have the Phi marketing model right here, and then we have the Emo Phi 128K model right here. And so now that we have our candidates, we also need to pick our method. And so of course, our method that we'll be using is DELLA, which, as a quick reminder, is drop and rescale via sampling with magnitude. So now with the models that we want to merge and the method that we do it, we need to now put together our merge configuration. Looking at the documentation here under the DELLA method, it says that the parameters are going to be the same as the linear method with the addition of a density and an epsilon and a lambda parameter. Density being the fraction of weights and difference from the base model to retain, epsilon being the maximum change in drop probability based on the magnitude, and lambda being the scaling factor for the final merged delta parameters before merging all of that with the base parameters. So knowing that this starts with the configuration for a linear one, we can go to their examples and check out the linear config. So here you see that you can put in the models, the parameters here for each model, which the parameters for the model specifically means the weighting of how much you want that model to actually affect the final merge model. So you can add in your own additional kind of scaling factor here of if you want more effects from one model and less effects from another as you're merging them, you can add that in here. And then of course the merge method and type. Adding on the expected parameters from the DELLA method looks a little bit like this. So now we have it all set up. We have our model as Phi marketing. I want to keep all of the effects of this on it. I have the model of the emotional intelligence one. Also want to keep all of the effects there. Our merge method is going to be DELLA, using our base model as the Phi marketing model here. And for the density, lambda, and epsilon, you can tinker around with different parameters for these, but I decided to just copy what one of the authors of the DELLA paper posted here as a configuration file example. So now that we have our config file set up, all we need to do is run some Mergekit processes. So I'll be using Google Colab as kind of my environment, but as mentioned before, this doesn't actually require a lot of processing power to run all of these things. You can do this with just CPU processes on a beefy laptop, or I've been running a lot of these iterations on my desktop gaming computer. But now that we have that set up, first thing, of course, that I'm going to do is drop over the config file into our environment and open up the terminal. And so setting up Mergekit is super easy. If you just go over to their repo, you can copy this installation block right here, and that will clone Mergekit and install all of the dependencies that are necessary to have everything running nicely. Awesome. So that took, a minute and a half maybe to get all of that installed. Now we've got Mergekit cloned and all of the dependencies good to go. Now all we need to do is type in mergekit-yaml, and then we can copy the path here to our config file, and then the output folder that we want our merged model to go to. So for this, I'll just put phi3 emo marketing example. Sending that off real quickly, it will go through and start to actually download all of the models that we need. So both the base model from the marketing checkpoint that we are using, and then also the emotional conversational intelligence fine-tuned phi3 model. And then it'll run all of the mathematic calculations to merge them together and pop it out into the phi3 emo marketing example folder. So I'll let this run and speed things up. Sweet, so now all of the actual base models have been downloaded here, and it is executing the graph, or merging together the models using the DELLA method now. Great, and just like that, we've merged them together. One thing to note here is that it actually could not load the tokenizer, but that's okay because we'll just borrow the tokenizer from the original phi3 mini 128K. So just pasted in some code that will allow us to run this model, and as I mentioned, it was saved in this file here, the phi3 emo marketing example file. That's where our main model is going to be. As mentioned, it didn't copy over the tokenizer from the original phi3 mini instruct. So what I have here using the transformers package is loading the tokenizer from the original base model. And this should work great because our merged models are all using that same tokenizer. And then for our model, what we can do is actually locally path over to this specific file here to load it up. So let's run that, and it should put it right onto our GPU here. So it first has to download the tokenizer from the original site there, and then perfect, loading the checkpoint shards, which are both of these safe tensor files that contain our merged model. So now that that's there, let's actually generate some outputs. And my prompt here are, what are specific actionable ways to market hair products to technical software engineers with an emotional angle? Let's see if that's able to actually capture both the marketing and the emotional intelligence that we merged into the model here. Sweet, so here's the output. Let's go ahead and read it. We've got understand the emotional connection. Recognize that technical software engineers, like all individuals, have emotional needs and desires. They may seek products that make them feel confident, professional, and in control. True. Highlight the emotional benefits. Emphasize how your hair product can boost their self-confidence, enhance their professional image, and make them feel empowered in their personal and professional lives. Wow. Showcase success stories. Share testimonials and success stories from other technical software engineers who have experienced positive emotional transformations through the use of your hair products. Create engaging content. Develop engaging and relatable content that resonates with the emotional needs of technical software engineers. This can include blog posts, videos, social media content about that's a little bit more generalized. Offer personalized experiencing. Provide personalized consultations or virtual trials to allow technical software engineers to experience the emotional benefits of your hair products first. I do like the personalized experience. I'm not sure that a consultation or virtual trial is the most conducive to hair products, but nonetheless, our model actually output some text. So that tells us that it's working. Further, more professional evaluations would have to be run to determine how well this is actually performing, whether you have just a generalized evaluation or your own dataset task-specific evaluation to evaluate on any sort of fine-tuning downstream test that you're using. That's up to you, but we have a nice merged model. And since it's saved here in our files, we can use like our Hugging Face command line interface package to actually push this and upload it to the hub on Hugging Face. That being said, that's really how it's done. So I'll link this collab notebook in the description below that goes over all 4 of the different merged models and the different merged methods that I was using, how to actually load them, and then also the different method and the specific config file that I actually used to create these via Mergekit. So if you're interested in trying out some of these different methodologies and interested in how the different configurations are actually built, give this a shot and tweak it to your own needs and desires. If you enjoyed watching this video, feel like you learned something interesting, consider supporting the channel by dropping a like, asking a question in the comments, or subscribing if you want to see more in the future. Thank you, and have a great day.